Hi, my name is Matt Strassler. I'm a theoretical physicist and the author of a recent book, Waves in an Impossible Sea. And this book is about the universe and about how it interacts with daily life.
I have read your book not once, but twice now. Waves of an Impossible Sea reminded me of kind of almost a decade ago when I first listened to Brian Greene's Elegant Universe, and it made me kind of question everything around me.
Fantastic. That's exactly what the book was supposed to do, and I'm glad it had that impact.
Do you have a sense for why we're not seeing any aliens out there?
Oh, that's such a
Does
great
it
question.
seem like something?
The Milky Way galaxy, our star city of a trillion stars, is about 100,000 light years across, which means it takes light 100,000 years to cross it. Which means if you were traveling at 1/100th the speed of light, which is not that fast, you could cross it in 10 million years. So if a civilization was born on some planet on the other side of the galaxy and they started colonizing the galaxy, they would have been here after 10 million years. But the Earth is, 4.5 billion years old, and the universe is 14 billion years old. The galaxy is probably, 12 billion years. Maybe we don't know exactly. Why haven't there been lots of civilizations forming on these different stars, colonizing the galaxy, showing up here, leaving artifacts around for us, leftovers that we would have found by now? So that's Fermi's paradox. Where is everybody, right? And this is a really great question. And so it forces you to ask, okay, what are the assumptions that go into this argument? It's a sensible argument, but it's based on a lot of assumptions. So what are they? Well, obviously, there's one possibility, which is life is extraordinarily rare, and we are the first life, or at least the first intelligent tool-building life in our galaxy.
Yeah, that one doesn't make sense to me. I feel like we should.
It could be. I would never suggest that we're alone in the universe. The universe has got 100 billion galaxies, right? So,
but even in our galaxy, we should have come.
There's a lot of stars. And now we know that most of them have planets in it. So, okay. So, what are the different things that could affect this? So, I think what's important to understand is that while it is true that we are a tool-building and now spacefaring species, there are a lot of things along the way which might be unusual, right? We don't have a lot of other intelligent species that we can study to find out what is the typical behavior of an intelligent species. So here's one thing which I think is worth remembering, which is that while it is true there are a lot of planets around habitable stars, not all stars are stable. In fact, most red dwarf stars, which are most of the stars that are out there, may actually be pretty dangerous in the sense that they flare a lot and they might kill off the life on their surface. Now, does that mean that they don't have life? No. We know in our own solar system that there are moons around planets nearby that have subsurface oceans, and they're protected. In fact, that's a really safe place to be because the habitable zone on the surface of a planet is a narrow zone. You can't be too close to the star and too far from it. But if you allow yourself to live underground, you could live in a lot of other places. So that would suggest that most life in the universe is probably subsurface, not on the surface. Much more dangerous than the surface.
So but if you live there's lizard people.
Okay, but if you live underground, will you have eyes? No. They won't be lizard people because they'll be blind. Why would they have eyes? What would be the point? There's no light.
Okay, so first of all, there's a bunch of aliens that are living in the planets and don't need to go into space or send radio signals.
First of all, they don't even know the stars are there until they develop technology which allows them to poke through the surface, which is no trivial matter if it's 100 kilometers thick. And it would be pretty hard, not impossible, to build spacecraft that can transmit. You just think about the layers and layers of technology you have to develop if you're intelligent in subsurface to send something to the stars that you don't even know are there. You first have to discover the stars. Even your own star is not trivial, though you can do that with a neutrino detector. But we can see the sun in neutrinos. So if you learn about neutrinos, you could actually discover the sun. But to discover the other stars, that's pretty hard. So just even the aspiration to explore the galaxy that you don't even know is there, it could take a long time to figure that out. So that's one issue. Another issue is that, we humans are tool building. But there's a lot of intelligent species on this planet which don't build tools. Or don't build a lot of tools. Whales, we don't know how smart they are. They're obviously pretty smart.
Mm-hmm.
They spend a lot of time communicating. We don't know what they're saying, why they're saying it. But, making tools, boats, making things that can allow them to go above the water and float around. They're not interested. Why are they not interested? I don't know. Are they capable of it? Maybe it's because
Yeah.
they're not capable, or maybe it's just because they're not interested. Maybe most intelligent species are not interested in exploring. Maybe that's a particularly human trait and it's unusual, right? We don't know that. Um, then there's the fact that we have hands. Hands are really good for making tools. Flippers are less good for making tools. They're really good for swimming around in a subsurface ocean. So if you don't need to make tools to survive, you may not have the ability to make tools in the same way. It may be much, much harder to develop the sort of technologies that we take for granted. Okay, then there's the issue. What are you going to do with those tools? We as a species, well, we have, at least some of our societies have turned out to be very greedy and very exploratory, and we like to build stuff, and then we like to use that with the stuff we built to get more stuff, so we can build more stuff. And how intelligent are we? Because we keep building stuff that makes our lives more and more difficult, and which makes things more and more
That's a good
dangerous.
point. Yeah.
Whereas the really intelligent species may figure out this is a bad idea.
Oh, that's a new twist to the Fermi
Okay,
paradox I
so
haven't heard.
right, the really smart species may say, "I don't want to explore." And then here's another thing: do you, Dylan, really want to explore the galaxy? Because when they send you out there at 1% of the speed of light, it is going to be 100 years before you reach that
Yeah,
star.
and I'm not sure I
Is that
want to
how?
see what I
Is
find
that how?
either. Like,
And then you may find that's not a really good place to hang out. I mean, you are leaving behind all the people, all the individuals in your species that you ever knew, and the planet on which where you evolved, where you are perfectly fit to go to planets where the atmosphere is poisonous, where it takes you 100 years to get there, where you're stuck on a spaceship with maybe, I don't know, 10,000 other individuals. You can't go home. You can't go out. There's no place. You can't go on vacation. You're stuck in this thing with no place to go. If anything goes wrong, you die.
yeah, maybe
Do
it
you really
just
want to
doesn't
do
make
that?
sense. Maybe it just doesn't make sense to explore the
Who
universe
wants
for
to,
anyone sufficiently intelligent. Yeah.
now, if you figure out how to go faster than the speed of light, okay, that changes things. But all the evidence is the universe is going to make that impossible. And so if you really have to explore the universe at a fraction of the speed of light, then you start asking yourself, does a really intelligent species actually have a lot of individuals that actually wants to do that? I'm not sure.
Do you think we're going to discover somewhere in this like kind of wave world that there are signals and maybe they are being created by someone else that's intelligent and it's not just sort of a physics pattern?
Well, here's the problem. The speed of light is not like other speed limits. Okay, now, speed of sound was thought once upon a time to be a practical limit, that, you couldn't make a plane that would go fast at the speed of sound because the stresses would break it apart. That turned out not to be true. You can actually go faster. But the reason that that's a meaningful statement is that when you talk about the speed of sound, you're talking about the speed of sound relative to the air. And air is a physical system. You could say whether you're stationary or not with respect to it, because you can tell if you move through it, you feel wind, right? So what you really mean is if I go through the air fast enough that I feel the wind of whatever it is, 1,100 feet per second,
Hmm.
can I go faster than that? That's a meaningful question. And if someone yells, can I hop in my supersonic plane and catch up to the sound waves from their yell? The waves from the yell are going out. Can I speed up and catch them? That is the way to think about sound. Light is different, fundamentally different, and so different that it took a genius, namely Einstein, to figure out that what I'm about to say is even possible. Because what Einstein realized is that, now he didn't actually realize this experimentally, but he guessed that what must be going on based on what he knew about light and electromagnetism on the one hand, and about Galileo and motion on the other, is that it must be that if someone flashes a flashbulb and light waves now start traveling out, and you hop in the fastest spaceship you can find, and you try to catch up with those light waves, you got the most powerful engine anyone can imagine. You turn up your gas, you go and you go and you go. From your perspective, the light will seem to speed up, in the sense
Yeah.
that you would think that if you're going faster, you should be catching up with the light,
It's always going to be
but
fast.
you don't.
Yeah.
It's like being in a nightmare. The faster you run, the faster the light runs. And What that means is that the speed of light is not like the speed of sound. The speed of the sound waves that are rushing away from you as you go in your supersonic spacecraft or nearly supersonic spacecraft, you're catching up with them. You cannot catch up with light waves that have passed you. They will always be moving relative to you at the speed of light, which in some sense is I mean, it's so bizarre when you say it that way. It's important to emphasize it's not really light that is important here. What this is telling you is not something about light. It is telling you something about the universe and the way that space and time actually work. The way space and time work makes it impossible to catch up with light, and therefore it makes it impossible to pass it, which makes it impossible to travel faster than it.
What is stuff? Like what is matter? What is this thing I'm sitting on, this world I'm in?
It turns out to be a huge question, which scientists have really spent 100 years or more answering. And we all learn in school that stuff is made from atoms, and the atoms are made from subatomic particles, but that's usually as far as we go. We never really worry about, wait a second, what were the subatomic particles and where did they come from? And the image that we then get from our chemistry class is that, okay, you take these atoms and you put them together and you build stuff. And it's kind of like building a sandcastle out of sand. You have these little objects, like little balls, and you just connect them together, and somehow you make these structures. And so presumably it's the same with subatomic particles. We imagine they're just like little grains of sand, and you just build everything out of them. Or the way you build, you build a snow sculpture out of flakes of snow.
Mm-hmm.
And it's a great way to think about it in the sense that it's very intuitive. We actually do these things in life, make things out of little grains. And it's so intuitive that it was the way that scientists imagined the way the world was for hundreds of years. And in a way, the idea goes back to the Greeks, who had the idea that, yeah, the world's made from these little ball-like objects. And it turns out, though, that that's not quite the right picture.
But that seems so wrong, It doesn't feel like that at all to me. But that's why
Which
this
part?
is fun conversations. Well, the fact that things aren't built out of things, like things are built out of bricks, they're built out of grains of sand, they're built out of solid objects. But now
Yeah,
I've learned there's a lot more to that
it's
story.
not true. And the flip side of that, which you might not think is part of the same question, is what is the absence of stuff? And what if you take a box and you take all the stuff out of it? What's left? And the obvious answer is, well, nothing. I mean, you go out in space, far from the Earth, far from any of the planets, and you ask, what do you have there? If you have a box of something, it's a box of nothing. I mean, nothing in there. But that's not true either. And so these two different surprises turn out to be related. That no, matter isn't really like grains of sand, and no, ordinary empty space actually isn't empty in a certain sense. So so what should we really think about instead? And that's really the where the book begins. And so here are a few things to think about that are very surprising. So, when you look out in the night sky and you look at the universe, it sure looks empty, and it sure acts like it's empty. I mean, the Earth is flying through space without, running into anything. It's just moving around out there. And we call it empty space. Right? So everything about it seems like it's this empty container in which stuff happens and stuff exists. But let me suggest something which sounds completely crazy. Imagine that I told you that no, the universe is actually full. It's full like the Earth is full of rock, or like the atmosphere is full of air. It's packed full. It's a material. Okay, I'm not going to stick by that all the way through this conversation, but I at least want you to think about it. I would naturally say, that's crazy, because I mean, I can move through empty space, the Earth can move through empty space, but if the universe were made of rock, how could the Earth move through it? And similarly, how could if the universe were like the atmosphere? Well, I mean, when I try to run through the atmosphere, I feel wind on my face,
Right.
but the Earth is going through going around the sun at many kilometers per second, and we don't feel anything. So
Yeah, like when they talk about how like a fish wouldn't know they're swimming in water or we're in air, like where there's something there.
yeah, I mean, when you say fish, we don't notice the air, but we sort of know it's there if we pay attention. Which is, the Greeks could figure it out. They noticed that if they can make a vacuum and that's the absence of air. And you can feel the wind on your face. I mean, there's things you can do to tell that even if you're a fish, you can feel the water's there. If you might not know what it is, and it's true, you don't usually notice it, but if you work at it, you can tell. But here I'm talking about something even more subtle, which is that even though you and I can't go through solid rock, there is something that can. It goes right through the Earth without slowing down, no friction,
What,
and
X-rays,
that's
neutrons? What?
nope, seismic waves, earthquake
Oh,
waves. If you have an earthquake on one side of the Earth, the waves from that earthquake go right through the Earth and get picked up on the other side by seismographs. This is how
but all the atoms stay in the same place.
the atoms stay almost in the same place,
Yeah, they
because the
wiggle.
seismic waves are making the atoms ripple. These seismic waves are ripples in the rock,
Mm-hmm.
and the ripples in the rock have no trouble going through the rock. They really don't notice the rock is there because they don't feel it. They don't slow down. Or sound waves, the sound waves that are crossing this between my voice and the microphone. They're moving through the air as though the air's not there because they're vibrations of the air.
Right.
So it's possible that the universe is full as long as the light we see is in some sense a vibration of the universe, so it goes through the universe without noticing. And as long as we and everything that the Earth is made of is in some sense vibrations of the universe, so it can just glide through the universe without any problem. Now, so
Yeah,
this is
real quick. Like, so I
yeah,
remember one part in your book that was like, that really caught me off guard was when you talked about how you could throw a rock at a cup and it would knock it off like a stand. But you could also attach a string to it and wave it. And the wave itself has enough energy to knock the cup over. And it kind of really hit hard. Even though I sort of knew that intuitively, I never thought like, oh, that's energy. That's something sort of solid that can push other things around that maybe is a little closer to matter than I expected.
right. The fact that waves can carry information and energy from place to place, it tells you that they're not as different from particles in certain respects as you might think. A ball, you can carry information on a ball by you write the information on the ball, throw the ball. The ball carries the energy and it carries the information. But we use light waves to carry both information and energy all the time. So we know that waves can do that. It's just that it doesn't really occur to us, for reasons we'll get back to, that that could actually apply to matter, to the or to atoms and the things that we're made out of. But it does.
hmm But yeah, but as you're saying, like when the wave goes through something, it kind of wiggles a little. One another example in the book was when you said at a football game, people might do the wave. Everybody
Right.
sits in their same seat, but they wave, and that wave moves around.
The
But yet,
wave goes around the
yeah,
stadium, but nobody's running around the stadium. The wave
right.
goes much faster. So when you have a medium like rock, which seismic waves are moving through, or like air with it, where the sound waves are moving through, or like the ocean, which is maybe the most familiar with it, the ocean waves move across the ocean. The ocean, the water isn't flowing in the same direction that the waves are. The water's just staying still, except for little fluctuations like this. But the wave can move from one side to the other without the the substance that underlies that wave moving very far at all. And so it's possible for the universe to be this sort of material-like thing. And again, I'm not going to swear it's a material for reasons I'll explain later, but it's acting like a material in the sense that it can host waves, and those waves can travel at tremendous speeds and do all sorts of interesting things without the space itself having to do that.
Okay, so do you feel like you've explained what nothing is well enough?
Well, I think one of the other things that's important to emphasize here is that, what I'm just telling you about the possibility the universe acts like a substance, and that we act like the substance that, and the things we're made of act like waves in that substance. This is not sort of new speculative idea. What I'm doing in this book and in this explanation is I'm trying to crystallize and characterize things that particle physicists have been learning over the past 75 years. It's the language of what particle physicists call their standard model. It's a set of equations that we use to explain all the things that happen in particle physics. It's an incredibly successful set of equations, predicts everything that we've been able to measure without exception. And so what I'm doing here is trying to give you a way of looking at those equations without actually working through them.
Yeah, the visual for it.
And they lean much more towards this idea that the universe is full and that objects are waves than that the universe is empty and that objects are made from little dots.
Okay, so let's jump into space for a second. Like when I see these videos of astronauts like handing like ice cream to each other, like astronaut ice cream or whatever, they just push it and the ice cream just floats across the space station and then the next person grabs it. They don't throw it like the way I throw a baseball. And that makes me think that there's no medium that it's going through. It's not going through water, it's not going through air, or at least for some reason there's no resistance. And as far as I understand at all, like you could push that thing and it just goes off for infinity. Is
Well,
like can
yeah,
you
I mean,
yeah, or
there's a
where's
lot of
that
things.
energy come from?
There's a lot of things in your question. So let's take it real simple because there's we can make it very complicated if we're not careful.
Okay.
But let's imagine an astronaut who's out somewhere far from the Earth. They're just floating out there, and there's another astronaut not far away, and but maybe a few miles, not far away by space standards, but quite some distance. So the astronaut needs to throw something a few miles. How hard do they need to push? The answer is
Not very
as little
hard.
as they want. They just, how hard they push determines how fast this object will start going. But once they let it go, there's no friction in space. It will keep going. This is in contrast to our intuition on Earth. And this is something which humans were confused about for tens of thousands of years. It's not a small matter. It took geniuses to figure this out, right? So we should.
But didn't you say there's a space of empty region of space has a lot of stuff in it, and none of that causes friction?
None of that causes friction, and that's the discovery that is true, and it's not obvious. The discovery that this is true was made by none other than Galileo. I mean, we're talking real geniuses here. And Kepler, who was living around the same time, didn't know this, didn't figure this out. So this was a major discovery in human history, was that the way the world works is that space, empty space, does not cause resistance. And therefore, if you push something through it, it will continue forever. That's capitalized, not in so that's characterized in Galileo's principle of relativity and in Newton's first law of motion, for those who've gotten that far in their science classes. But the general point is that this is a very hard thing for us as humans to understand, because everything that happens on Earth contradicts this principle. Right? If you want to push a box across the floor, you don't just push it once and then let it coast. It'll slow down and stop immediately. So you have to keep pushing it, right? But that's because of the friction from the floor. And you can get some sense for that if you imagine that instead of pushing it across the floor, you went to a lake that was frozen, and you can put a little water on the ice, so it's really slippery, and then you gave the box a push. Well, that box is going to zoom halfway across the lake before the very little amount of friction will slow it down. Right. And if you go out into space and do that, where there's no gravity to pull it down onto some surface, and there's no surface, you just shove it, there's no friction. It will go forever until something bumps into it. And that intuition is very foreign to us on Earth, where first of all, there's friction, and second of all, there's gravity. So anything you throw will eventually hit the floor where there will be friction. And if you throw it hard enough, there's also friction from the air resistant.
Yeah, for 4 billion years, all of our ancestors had to deal with friction. So it just
our minds are designed to handle living on Earth. They're not designed to handle living in space. So all this stuff is counterintuitive. It's not something we're hardwired to understand. It's not something we grow up intuitively learning. And so it was something which, for people to figure out before humans went to space, took an enormous leap of imagination, and that's what Galileo was capable of. And so he wrote this famous book in which he talks about the fact that if you were inside a ship that is moving smoothly through the ocean, steadily with no waves, just gliding through the ocean. Sure, if you're outside on deck, you're going to feel the wind, you're going to see the ocean, you'll know that you're moving. But if you are inside and there is no way for you to look outside, there is nothing that you will feel and nothing that you can do. No experiment that you can perform inside that smoothly floating ship that will tell you whether you are stationary or you are in motion, or even which direction, whether it's going forward or back. You won't know. And this is hugely important because before people knew this, there were very smart people arguing that the Earth could not possibly be spinning and it could not possibly be going around the sun, because we would feel that.
Yeah,
but everybody knows you can feel it when you're moving, except that when you think about it carefully, what you feel when you're moving is you feel the bumpiness of the road. or you feel the bumpiness of the train tracks. You don't actually feel the motion. And where you discover this is when you remember that we're going around the sun at 30 kilometers per second, 20 miles per second, and we don't feel it at all.
Yeah.
That's amazing,
Have you ever
but it's
heard that
true.
like if the have you ever heard that like if the Earth was just like stopped or paused, we would fly off the planet? Like, is that
Sure,
true or is that fake?
if it were suddenly stopped,
Yeah, like
yeah,
just magically everything that's like material rock underneath
that
us
would
just stopped.
it would be no different from riding on top of a car if the car hits a wall. You will go
You would
flying.
just go for it. Okay.
Or when you're biking and the bike hits a wall. And the reason is that it's not that motion is an illusion. It's that you can't tell the difference between being stationary and being in steady motion. But if your motion isn't steady, you can tell.
But it's equally valid to say that I kept moving. If the Earth stopped and I flew off it, it's also equally valid to say I kept moving and the Earth stopped, right?
It's a
Everything's
great question.
relative to itself.
Not quite.
Oh.
And the reason is that there is a difference. What you can't say is, for example, let me give an example of something where indeed it's ambiguous. If I'm in steady motion and you're in steady motion, we can't say which of us is moving or whether we're both moving. But if one of us was moving and then stops, that means our motion changed.
Oh, you can
And
measure the change on
that can
which
be
one.
measured. So the change in motion can be measured. What can't be measured is steady motion. You can't tell if you're moving or not. But if you stop,
But you could pause me sort of magically, and the Earth would keep spinning, and then the wall would hit me.
well, right. So there's a big difference between the Earth hitting a wall and you going flying, and you hitting a wall and the Earth continuing
Yeah.
on.
Like if
That's a
I
very
just
big
stopped,
difference,
then the rest
right?
of the
And
planet would spin around me, and something would hit
the
me.
difference is in your
Yeah.
bones, right? I mean,
Yeah.
the sudden stop will break your bones. It's a
Yeah.
real physical effect. So it's not a statement that all motion is illusory. It's the statement that steady motion is the same as no motion, which is crazy,
It is very
but
crazy.
true. We don't know why this is true, but it seems to be a fundamental principle of how the universe works, and it's the oldest principle of physics that hasn't been revised ever in the last 400 years.
Yeah. Well, another part of the book that kind of got me sort of rethinking my normal assumptions was I often imagine things in an XYZ coordinate system, right? Like I can imagine sort of a shoebox and you could put a dot in there. It's just more of like the way you would make a graph or a scatter plot. And
Right.
I've always, and especially with like artificial intelligence, a lot of time you're talking about things that are like adjacent or to one another, basically positioned. And this idea that space and Earth and the sun are all kind of could be in some sort of gigantic shoebox with an XYZ coordinate system always was in my head. But now I'm starting to think that one of the things I picked up from your book was that it's not quite like that. Like there isn't, if everything is really relative to each other, there is no true XYZ that would be universal, right? So is space like the whole universe isn't on in like one continuous plane that could be measured? Everything
Well,
has to be from one spot to another, right?
yeah, I mean, I think what you're grappling towards is this issue about whether the universe has a natural coordinate system where you'd say, okay, here's the center, and here's natural directions for forward and back and east and west and up and down, and I'll leave that center there, and I'll measure everything relative to that. And
I always thought the
if
Big Bang might be the center and everything was
right,
out from that.
and that's not the way it works. And of course, it's very natural for us humans to think that way, but the facts of the matter are somehow much more subtle. And so, first of all, there's the point about the Big Bang is not really an explosion from a center. It is an expansion of something that is already somehow spread out, and we don't know enough about the birth of the universe to know exactly. I mean, the Big Bang theory in this case really is ambiguous because we understand what happened running the universe backwards in time up to a certain point, but at the very beginning we lose sight of what actually happened, so we don't really know. But what we do know is that the expansion of the universe that is going on today is not to be thought of as an expanding fireball into emptiness. Instead, it's the whole thing, it's kind of the whole thing spreading out. And so there's literally more space in the universe today than there was a billion years ago. It's actually an expansion of space, not an explosion into space, which is very strange to think about. But when you start thinking that, well, space is kind of like a material, maybe it's a little less strange.
But is it still a coordinate system like a shoebox that's
Okay.
just getting bigger and adding spaces between every space? Or is that not even right?
Well, one of the lessons of the weirdness of space and the weirdness of motion is that a question like yours is somewhat ambiguous, because how we choose to lay out coordinates across space is kind of up to us.
Yeah.
If there isn't a center, then there is no natural, obvious way to do it. So we have to choose what is our point of origin for our coordinates? How fast is it moving relative to you and me? We could make, I mean, are we stationary with respect to that coordinate system, or are we moving? Well, I don't know, right? And how should I orient it? Well, that's up to me too. So um, one of the things we learn is that the universe is in some sense very disorienting, because it doesn't have a natural grid. It's not like, there's a city here and I can sort of say, okay, here are the streets and here's the center of town. I can lay out a grid however I choose, but the universe doesn't come equipped with one.
Yeah.
It's a choice that I make.
Would they match up though? Like if you were on Alpha Centauri and I was here, or maybe something way further away than that, and then we mapped the universe, would we still see gravity warping it in the same way? Like would our maps align, or would it be because of physics impossible?
There are certain things that would align and certain things that wouldn't. And indeed, one of the jobs of theoretical physicists is to make very clear for themselves which are the things which would align, because those are the physically meaningful things.
Like rest mass, right? And those kind of things.
Yeah. For example, the fact that the distance between the sun and Alpha Centauri is 4.5 light years, whatever it is exactly, which can be measured by actually sending a signal from one to the other and then back again. That is something which can't depend on what coordinates you use. That's a measurement of a physical event where light went out and it came back. So that is an example of something which does have to match. But anything which depends on your coordinates and how you choose to describe things, that's a choice. And so one of the surprises of Einstein's physics is that there were a number of things that people thought were physical and therefore everyone would agree on, such as how long is this movie?
Which it turns out is not one of those tools.
No, it's not. And in fact, when you're really careful with gravity, each person has their own experience of time. There's no universal time to talk about at all. And distances similarly. So, again, if you define a way of measuring a distance by, I'm going to send a flash of light from Alpha Centauri to the sun and then turn around and send it back, that is a well-defined physical measurement. Nobody can disagree about that. But if you ask how long did it take and how much distance was covered, well, that could depend on a person's point of view, because that's the way time and space work in Einstein's universe. So it is quite tricky, and indeed physics students spend a lot of time learning how to identify what is physically meaningful and what is just dependent on what coordinate system you happen to have chosen.
I am ready to switch gears into a little bit more abstract, a little more kind of fun thoughts for me. I play around with this idea that I might be in a simulation. Like sometimes it's a talking point on social media where it feels like we're in the Matrix, or like the universe is glitching out, or like we're building these simulations, especially with artificial intelligence, that seem so real. I have to sometimes wonder, like, will this keep advancing to the point where those characters feel like they're alive in the same way I do and they start exploring their environment? So if you wouldn't mind, maybe we could kind of dive into sort of a fun thought experiment. And my questions are similar to what I learned in the book, but I wonder, like, if, say, like a video game like Mario 64, like a 3D game with Mario and Luigi in it, if they were to become sufficiently aware and sort of free to kind of look around and measure things, do you think there would be a kind of, quote, like source code that they would discover that would be anything similar to the kind of source code that seems like it might be behind our reality?
Well, this is really interesting to think about, because it brings up a lot of different issues about what is similar and what is different about maybe not computation in general, but the kind of computation that we do and the kind of things that the universe is doing, which is not to say that the universe is not a simulation. It could be, but the way it works is quite different from the simulation that Mario Brothers are living in. If you were in a video game like the ones that we write today, and you were sufficiently smart and had experimental measurements were something you could do, then yeah, there's no reason you couldn't learn the rules of your game.
Yeah, and
I
think of how
mean,
clever Mario is. Like he's a plumber, he's got
uh,
tools. Like he'd be wondering what's
he
this
he
castle
he,
made
he
of?
would
Like
be,
what does a
yeah, why
Goomba
not?
do?
And we're very good at reverse engineering, right? If you find yourself in the middle of a game that you've never played before and you're just watching it play, you can probably figure out, oh, that's what the point of the rule. Oh, there's this rule. And I mean, it's not easy to figure out how football is working if American football is working if you've never been in the United States before, but you could probably do it if you watched a bunch of games, right? If you were systematic about it, really
Hmm.
careful, you could do it. So there's no reason that Mario can't sort of figure out, um, these are the rules by which my body works, and these are the rules that apply to the walls, and these are the rules that apply to the floors, and these are the circumstances in which I could do this, these are the circumstances in which I could do that, and these creatures have these limitations. And so, but if you think about it, all of this is at a relatively high level. There are these objects in the game, and they follow certain rules. Now, when you think about how our world works, there's you, there's me, there's the walls, there's the floor, there's the air, there's the light, so forth. Everything follows the same rules, all of it. And
Right.
rather than those being rules that are sort of like, okay, Mario can't go through walls, but he can go through this kind of door. These rules are written at the level of, here are these wavicles, these photons, electrons, and here are the forces that pull them together. Or really more detail, here are the fields of the universe, and here is how those fields interact. It is very, very far from the question of, well, what am I as a human being allowed to do, and how do I interact with the wall?
Right.
And in the programmer's mind, as they are designing Mario's game, Mario doesn't have to follow the same rules as the wall. And the rules of the wall could change, and Mario's rules could stay the same. And these things are independent because the rules are at a very high level. They're at the level of the macroscopic objects. It's a very different thing to build a world which is entirely built upon microscopics, which is the way our world seems to work. And so, whereas the programmer says, I want a game with walls and Mario, the universe says, I have some very basic rules involving fields. Let's see what happens. And so, you and I are non player characters, right? We weren't
Yeah,
put
we're
in,
NPCs. Yeah.
we come out, and we weren't put in by the programmer. We emerged over billions of years of evolution, and there was no guarantee that we would exist. And so nobody who wrote the original rules gave us any rules. Our rules are inferred from the way we are constructed from the basic microscopics.
Okay, but what if it's like an NVIDIA supercomputer and
Yeah.
they started a simulation that was like essentially 4 billion years ago and it's just been playing out and it's not like maybe not like Mario where somebody created a goal for it, but there was a simulation that was basically everything you would measure would follow from that simulation. Would that be similar to what we see in the universe deep down?
Yeah. I mean, a simulated universe and a universe that is not simulated might be indistinguishable from the inside. And in a sense, this is, scientists do this all the time on small scales. I mean, we can't actually simulate the universe, there's too much going on in it. But astronomers simulate the history of the universe and the formation of galaxies and so forth. They don't do this by starting at the atomic level. That's too hard. But what they do is they do some math and some reasoning to gather to sort of simplify the rules of the universe without losing key pieces of information. And then they place down some initial objects in some sort of rough pattern with some fluctuations, and they turn on gravity in the simulation, and then they just let it run, and they see what happens. And so, uh, they are capable of sort of understanding roughly what happens in a universe that has the properties that we think ours has, and they're capable of seeing what happens in a universe whose properties are somewhat different. They could use that to say, okay, we're pretty sure that in a universe with no dark matter, the structure would come out wrong, and that's why we think there's dark matter. That is a
Yeah.
simulation of a universe. But again, it's dramatically simplified compared
Yeah.
to the simulation that
But
our universe is running.
do you think if it runs long enough with enough computation and it's even more accurate than what our current computers can do today that we're going to see life emerge in that simulation?
There's no reason why not. I mean, if indeed, as we think, life is an outgrowth of natural microscopic processes over long periods of time, then if you simulate that, then it should appear in the simulation. To say it another way, if you had a computer which was powerful enough to simulate maybe not the whole universe, but everything that happens on the surface of the Earth and its interaction with the sun as you have the weather and so forth, yeah, why wouldn't it show up? That's sort of the claim,
And would
right?
those simulated humans, when they started learning about the most fundamental elements, would they find waves or particles?
Whatever the rules are that are built into the this basic simulation, they would be able to uncover. Now, what they wouldn't be able to uncover is what are the rules of the computer that's running the simulation, right? Mario has no access to the NVIDIA card, the GPU.
Right.
There's no way to make an experiment on that because that's not in the simulation, that's outside it. So if our universe is a simulation, we can indeed understand all the rules by which it operates as long as there are rules that it sticks to.
If it's like a video game like The Sims and they look around and they measure their universe, they probably won't find pixels because that's how we're looking at them. But they would find something, right? And I'm just trying to get my head around like, would that something look anything like a wave? Like for us, it's math, and then it's logic gates, and then it's a simulation, but like they can't go all the way down to that. But would they see something discrete or something wave-like? Because it's clearly a 2D chip that's creating their 3D environment.
Right. Now, back me up again. Though. Which case are we talking about? Because are we talking about a typical video game that we have today?
No, let's do it like simulation. Yeah, because
Okay.
no human involved in the narration of the storyline, like something like a simulation.
So if you have a real simulation of a universe with microscopic rules,
and life just emerges,
and life emerges from it, and they can do experiments which are self-consistent within those microscopic rules, there is no reason they can't reverse engineer how they came to be.
It just seems to me interesting that like I feel like there would be a lot of things that would be relative. Like if I imagine a character that's in a 3D game, I think they would think they're in 3D at first. They would evolve in something they would think is 3D, but they might start realizing that like, oh, actually it's relative. Like a wall when I go forward or back is sort of relative to like where I am when I measure it. And then that kind of makes me think like, oh, is our universe something like a simulation?
Well, again, so this touches on the question of rules. If there are rules and those rules are stuck to all the way through, then that character in the game can discover them in principle. Now, they might not seem that sensible. Again, in a full simulation, presumably they'll be sensible, but in a typical video game where the walls might do some kind of funky things, as long as those funky things are regular, that they're always the same every time, the player can discover that. Now, the player may not be able to discover why it does that because it was decided by some programmer who's outside the simulation that that's the way I want to program it. It's not some sort of coherent set of rules as in a full simulation where there's a coherent set of rules you start with and everything obeys them. And it seems that our world is like the second. There's a coherent set of rules at the microscopic level that everything seems to follow. So far, that assumption, that's a hypothesis, but we have no evidence that it's false. And so far, using that hypothesis, we've been very successful in finding equations that describe the world.
So, like, if things aren't particles sometimes and they're more waves, is there still a notion of discrete? Because I've also heard things about like a Planck length of time, a Planck length of space. That seems to me like it's still component-wise, even if I could go into a wave, it feels like you can zoom in infinitely, but there would be a limit.
There's two elements to this. So this is an important point, though. So when we say that when I say that an electron is not really a particle, that does not mean that it is not particulate in the sense that an electron is indivisible. So I can have one electron, two electrons, 3, 10, 17. I can never have half an electron.
Oh, they don't blend together at all.
They do not. They come in units. Same with photons. Particles of light, you can have any number you want, but it's always an integer number, always 17 or 14 or 192.
Didn't you say in the book that electrons are indistinguishable from each other?
They are also indistinguishable. That's a separate, an additional issue.
Okay. Walk me through everything.
Yeah. Good. So the fact that they're indistinguishable is really interesting and not obvious at all. But the fact that they are indivisible is the first really important fact, because that means that in every atom, every type of atom, we could say exactly how many electrons it has. When I tell you that oxygen has 8 electrons, it has 8. It doesn't have 8.2, doesn't have 7.96.
It's not a
It
spectrum.
has 8. And that is critically important because that what that means is that every single oxygen atom has 8, which means it has exactly the same chemistry, which means that when you breathe, it doesn't matter which atom of oxygen happens to hit which particular part of your lung. It can accept any oxygen atom because they're all the same. So it's really important that electrons are units, come in units, that they're all the same, and that they're indistinguishable. And why are they all the same? Well, that comes back to the fact that not only are they waves, they're waves of a field called the electron field. And okay, it's a little bit of a longer story than we can tell right now, but this is basically the statement that, look, you can't tell the difference between one ocean wave and another. They don't come with labels. And whereas particles, you could, sort of, I'm going to take this particle, I'm going to mark it, I'll make a mark on it, I'll make a mark on that one. These two particles, you could mark them, and maybe they would be easier to tell the difference. But electrons are all the same. They're all waves in an electron field. There's no difference between one electron and another. So they are identical, and so they can't be distinguished, and so they're interchangeable. And that turns out to be important in many, many different senses. One of which is that all oxygen atoms are the same.
The Planck length. I was wondering like how that kind of fits in.
Right. So this is a statement about the discreteness of particles, right? Wavicles or particles, whatever you want to call them, they come in discrete units, and that's why the word particle is used for them. Now, when we start talking about empty space itself, does space come in units? And are those units like voxels? That's much less clear. We do not know. And
that's an unanswered question.
That is an unanswered question. We have no experimental evidence for it. The theoretical evidence is actually probably leaning against there being really sort of meaningful voxels, but it still may be meaningful to say that there are aspects of space which, although they're not really voxels, they're kind of voxel-like, maybe. The best thing to say about that now, I think, is that this is one of a number of speculations that physicists are playing with. What we do know is that there is something special that happens at a certain length. If we assume, and that's a big assumption, that there aren't some really important things about the universe which we haven't discovered yet. We just sort of take what we know about gravity so far, and we know about particle physics so far, we know about quantum mechanics so far. We know that you can take black holes and you can make them smaller. You can make smaller black holes, you can make smaller black holes, but the smallest black hole you can make will have a size that's known as the Planck length. And its mass will be the Planck mass. What are these lengths? Well, the length in question is ridiculously small. It's 10 to the minus 35 meters. So take a 0.0001 where there's 35 zeros in that. That's how small that's the smallest black hole you could make. We think of black holes as being big, but they can be small. They can be really small. And so it is believed that there must be something special that happens at the scale of the smallest black hole, because if we make something smaller than that, it'll act like a wavicle, like an electron. But if you make something bigger than that, it'll act like a black hole. So it's sort of a crossover point between different types of behavior. And
does it feel analogous to a pixel like that Mario and Luigi would find, or anything, or does it feel, or like the basic logic gates that would create reality, or does it seem like they're just very different topics?
They could be the same topic in the sense that, so let me give you a sort of analogy that fits in with some of the quantum computing stuff. So naively, when we think, okay, they're building things out of qubits, we think each qubit, okay, here's one qubit, here's another qubit, here's another qubit. But one of the things that's been discovered, not only by Google, but other researchers, is that you're kind of better off making your qubits not physically located, but kind of logical, so that the individual qubits are spread out a little bit, which makes them less sensitive to errors. So now it's still true you're talking about qubits, but they themselves are not literally little dots. And so there may be a sense in which the right way to think about quantum gravity is in terms of voxels of space, but they're not really literally voxels. They're somehow spread out a little bit, but they still keep track of this sort of typical scale of the Planck length in some way. So I suspect that there's some sense in which there is some kind of structure to space and time, but that structure isn't quite as naive as just a bunch of voxels strung together. Nevertheless, if you're trying to figure out how many voxels would you need or how might they behave, this sort of naive notion of voxels might still give you some intuition. Even have to be careful not to take it too far.
Is there any hints that if we could measure the universe on the Planck length of these voxels, like there would be errors or glitches that are getting smoothed out as we get bigger? Like, do you think there's some kind of quantum, what do they call that? Like a smoothness algorithm?
Well, this is a tricky question, because one of the things that makes quantum physics so interesting is that it is this weird mix of things that are deterministic, that is to say, determined, and things that are probabilistic, that is to say, statistical. And saying exactly where the line is between those two things is sometimes quite difficult, in the sense that people disagree on the right way to interpret what is actually what quantum math is actually telling you about quantum physics. So,
And like, is that error correction, do you think, that's happening that makes it go
well,
from one to the other?
no, probably not. But on the other hand, the quantum error correction codes that were developed, they were developed by a sort of by John Preskill, who's in my field. So I wouldn't say that these things are disconnected. Preskill's been thinking about particle physics and quantum gravity for many years. It's not an accident that he started working on this subject. So I'm probably not expert enough. I mean, there are people out there who are really thinking very hard about the relationship between um, quantum computing and error correcting codes and black holes, and how they work. And I'm just expert enough to know that I'm not expert enough to answer that correctly. So, but I could certainly point you to people who would love to talk about that. But I think that what's fair to say is that um, there are relationships here, but there's no um, there's as yet no clear statement that there has to be a really obvious and straightforward relationship. What does seem to be the case is that the relationship between voxels that sort of builds out space into a sort of a continuous whole does seem to have to do with entropy, and of the sort of the sort that one finds in quantum physics, and that space-time sort of emerges if you think about it that way, from interactions between quantum systems, and that's quite a strange notion, and we haven't figured it out well enough yet for me to be able to explain it in clearer words. There may come a time where we can do that.
What about the idea of a glitch? Like, does it feel like anything in the universe isn't adding up, right? I mean, there's certainly unsolved mysteries, but do any of them kind of intuitively to you feel like they're a glitch in reality? Like there's something where it's just like jumping to a place where it doesn't make any sense? Or does everything seem like it's kind of explained with asymmetries and waves and all of that?
This is so there's two types of glitches we could talk about. So let's distinguish them. There's always the possibility of a glitch that happens once, or happens a few times but completely randomly.
Hmm.
And a computer programmer can put that into a computer game. That's fine. But science has a problem with that, because I think
Replication.
it's important to understand that science is not, the results of science should not be equated to truth, because science makes an assumption when it starts. The process of science is to assume that there are laws of nature and do measurements and reverse engineering to figure out what those laws of nature are. Now, if there are things that don't follow any rules, you cannot discover them because you can't check how they worked. This is one of the reasons why, on the one hand, creation science is not science, because they violate the basic assumption of science from the beginning. But on the other hand, it doesn't mean that creationism is wrong, because I mean, I'm not suggesting that it's right, but the point is that, just logically speaking, science is not the same as truth, because you're making assumptions before you start science, right? So a glitch which violates the basic assumption of science is going to be very hard to discover scientifically, and we're going to be arguing about whether it's real or not. Glitches happen in experiments all the time, but that's typically, as cosmic ray goes in and mucked with a computer chip, or there was some sort of fluctuation on the electrical lines. Those are not the sort that you worry about if you think that's sort of consistent with that. But the point is, if there were a real glitch, you'd probably attribute it to a problem with your measurement. Now, if you have glitches which are weird but predictable, that is to say, maybe they're hard to predict, but they are predictable, then chances are you'll see enough of them that you'll figure out a way to show that they're predictable.
And have
Well,
you
then
ever
it's
come
part of
across?
science,
Yeah, have you
right?
come across anything like that in your research in your
No,
lifetime?
no, not really.
Oh, but so does the universe make remarkable sense to you?
Well, yes, no. So let me. I think the answer to the question I was going to give will in some sense address that, which is that you know we don't go in with the assumption that there are no weird things that happen. We don't necessarily assume that the universe follows the same rules every day. We just assume that it follows rules that are predictable, which means that there's some, let's say, there's some overarching rules which are predictable, but the kind of day by day rules they could be glitchy, sure, as long as those glitches are predictable, but we don't actually find that. So, for example, the Large Hadron Collider is the big particle accelerator in Geneva, Switzerland. It's running every day outside of the winter where the power is too expensive, but it runs, it's running every day, and it's producing collisions of a certain sort, and lots of different types of things happen in those collisions. And if one day the results of those collisions were wildly different, we would see that, but we don't. So
So it's pretty consistent.
what we find in experiments so far, run over several years, that there's no glitches there. Now, how else might we see that there are no glitches? This is another really important point. Suppose there was a glitch in which, let's say, for 3 seconds, just three, the proton's mass was increased by a factor of, let's say, 20%. And then it went back. What would be the effect of that? Would we notice? Yes, we'd notice. We would all be dead.
Okay. Okay. We'd
So
notice.
glitches are extraordinarily dangerous to life, to planets, to stars. You glitch around with the laws of nature, you destroy things permanently. So the very fact that we exist after billions of years of evolution is some post facto evidence that glitches are very rare and very small if they happen.
So when you smash the tiniest of particles together in these colliders and you look at what's inside of them, is it always the same thing that pops out and then we measure it over and over again, or is it kind of random and averages together? Like, do you sometimes get like up quarks and down quarks and then you like average that together to tell what's in them, or is it very like there's something
Right.
in there
So
that you get
this
every
is
time?
this is a great mixture of that determinism and randomness that's in quantum physics. So let me first emphasize one thing that is, I think, important to understand about why we do these experiments where we smash protons together. We are not interested in what's inside the proton.
Oh,
The point is that because of Einstein's relativity and because of the way quantum physics works, what we're really interested in is getting one particle inside of one proton to hit a particle inside of the other proton and undergo a process where they are transformed into new particles that weren't inside the proton to start with.
okay. So I got that
That's the
wrong.
key. Well,
Yeah.
no, but it's not obvious, right? But this is the heart of why we do particle smashing.
But I should
It's
have
not
known that
because
because they're not particles that can break open. We just talked about their waves. They should have been crests
well,
or whatever
protons
that like
protons are more
mixed
complicated.
together.
Protons actually do have stuff inside them, so we could be interested in that. And people in the past did, in fact, smash electrons into protons to find out what was inside a proton. So it's not that wasn't an interesting question, and we did answer. They have quarks and gluons inside them. But what we're interested in at the Large Hadron Collider, where we smash the protons together, is not the interiors, but in producing something new. It's like, it's a little bit like, imagine you could smash two rocks together and make a whale.
Yeah.
That's kind of what we do. We make top quarks, which are not found inside of protons by smashing protons together. We make Higgs particles. We make W particles. Those particles are not to be found anywhere because once you make them, they fall apart in an incredibly tiny fraction of a second. So the only way we know that they exist is by making them from scratch. And this is the way to do it. You smash these things together so you have a lot of energy in a very small space. And that energy can then be converted via the standard model's interacting fields into ripples of something else. So you send in ripples of one type and they interact and you create ripples of something else, namely top quarks or Higgs bosons. And that's the secret to particle physics. Now, then comes your question, all right, but do you get the same thing every time? The answer is no. We're doing the same thing every time. That's the deterministic part. But we don't get the same thing every time. That's the quantum statistical part of quantum physics.
But
So what quantum physics
is that only because they sometimes hit at different angles, and if you could be more
it's a
precise,
great
it would
question.
be the same?
The answer is no. It will
Hmm.
always have some randomness to it. And that's because of quantum physics. That's the nature of quantum physics.
Oh.
You can do the same thing over and over. And what quantum physics tells you when you calculate in the math is it tells you all of the different things that can happen, as well as the things that can't happen. And it gives you the probabilities by which this thing will happen and that thing will happen and that thing will happen. And so the reason we do these experiments over and over and over again is we want to measure many, many times so we can see if the probabilities come out right. So not only are we interested in top quarks, we're interested in how often do we make top quarks? What fraction of proton-proton collisions make top quarks? We have a prediction for that from the standard model, and we want to see if it's right. It is.
So is your gut that the universe does have a certain amount of like entropy or randomness into it, or do you kind of think I've heard like pilot wave theory would kind of be like there is something solid just beyond our kind of universe making sense? And I don't know, where's your gut kind of land on that?
Well, leaving aside the pilot wave specifics, I mean, you're touching on a deep question which nobody understands, which is how do we make sense of the randomness that quantum physics has inside of it? And Einstein was ridiculed at the time for not just somehow making himself comfortable with it, but there are many things about it to be that one can be uncomfortable with. And the question is this randomness um, a sign of something that we do not know? That if we knew it, then everything would be exactly predictable rather than just statistically predictable, or is it somehow inherent in nature that it is a statistical? There's something about it that's inherently statistical. And the only thing that we can say for sure is that if there is some way in which it is determined and not statistical, it's going to be really subtle. Because the most obvious ways that you could try to build a theory of that fail. They're inconsistent with experiment. This is one of the things that was pointed out by John Bell. He proposed an experiment which would show, and other experiments like it have been proposed, that would check whether there could be some simple way that the information could be stored somewhere, you just haven't accessed it. And you can show that no, that's inconsistent with what happens in quantum physics. But there could certainly be things that we don't yet know about how the world works, which could change our views on this. So I think that the mysteries of why quantum physics works the way it does and how in the world we can wrap our human heads around it remains,
Okay.
one of the
So
central questions.
there's not even enough evidence pointing in one direction yet that you feel like one is more likely than the other. It's
I
pretty
I don't
50-50 right
even
now.
know. Uh,
Or
I
it's like
wouldn't
the whole
even. I
question needs to be rethought, kind of.
the whole question is open. I mean, I wouldn't say there's evidence one way or another. I wouldn't say that it's clear even how to ask the question. Um, there aren't, some theoretical physicist needs to come along with a proposal that has an experimental consequence that we can actually check. And so far, most of the experimental proposals that I've heard, most of the theoretical proposals that I've heard, which have experimental consequences, they don't ring very well to me. That doesn't mean there isn't a good one out there, but I don't think that good ones have been found yet. So, this is often where we are in science, right? Most of the time in science, there's some things we figured out, and then there are big open questions. And sometimes there's no evidence one way or the other until the day you figure it out, right? So we may not know the answer to this question for centuries. Somebody might have an insight. We might discover something, in a decade that would change the way we think about it. There's just no way to know.
So we know waves are an important part of this book and the way that you've been explaining the universe. So there's a lot of musical metaphors, and those have resonated, no pun intended, with me for a long time because I can imagine how a guitar string could sort of be flat and you could grab it and sort of pluck it and it pops into like on a waveform, something that's very tall and then kind of like creates sort of like a bell curve type shape. And that also kind of feels like an electron or a particle, especially when I think about it in terms of like sort of quantum. But this idea of waves and resonance, does modern physics have more in common with like genres of music, than kind of the old billiard ball planets kind of particle idea?
Well, certainly the picture that is always drawn of atoms that comes from the Atomic Energy Commission and all the images that were used in the 1930s and 40s when atomic energy was coming up. It's an image of an atom as a set of balls, some electrons going around on the outside, and an atomic nucleus in the middle made of some protons and neutrons. And that picture of billiard balls and of grains and so forth, as I said, it turns out not to be really the way the world seems to work. What I can say about the relation with music is not so much that it's a relation of a type of music or a sort of harmony that we humans are used to, but it is a relationship with musical instruments in the following sense. So if you take something like a guitar, and let's not worry about playing it, just the fact that it's got 6 strings means that if I just pluck one of those strings, I'll get a particular tone. And so the guitar, if it's a 6-string guitar, it has 6 particular frequencies, 6 particular notes that it likes to play. And you could change them by retuning the guitar, but at any given time, it's got 6. Okay. The piano is 88. And different instruments have different numbers. They resonate in different ways. They have different notes that they prefer to vibrate at. And this is also true of the universe. The universe, if you whack it, has certain preferred frequencies. And those frequencies turn out to be very important because they're related to the masses of the elementary particles. That relation comes through Einstein's relativity and through quantum physics. So it's not a short story. It's indeed one of the main points of the book is to lay that out in a non-technical way. But there is a very real sense in which, even though I don't think you and I want to hear the music that the universe plays, it's completely out of tune. Nevertheless, the universe behaves a lot like musical instruments do. And again, that's not sort of some sort of speculative analogy. What I'm telling you is that if you write down the mathematical equations for musical instruments and how they vibrate, and you compare them with the mathematical equations that particle physicists use, there are a lot of similarities.
And if the world was tuned different, what would happen? Like the atoms would not be the same size, or they would have different energies?
Lots of things would change. Yeah, I mean, so for example, you could if you changed the frequency which corresponds to the electron, or more precisely, what that means is a stationary electron. If you put it in front of you, it's going to vibrate, and there's a certain frequency at which it vibrates. That special frequency is related to its mass. Why? Because thanks to quantum physics, the frequency at which it vibrates is related to how much energy it has. It has energy because it's vibrating, right?
Mm-hmm.
But E equals mc squared. So the amount of energy that it has is related to its mass. So there's this direct relation between what the frequency is and how much mass the electron has. So if I change the frequency, I'm going to change the mass of the electron. If I change the mass of the electron, if I make it larger,
then what? The whole periodic table changes? What happens
atoms
then?
get smaller and all the chemistry changes. And yeah, a lot of things would change. Wow. So, and if you make it, these details of particle physics have real direct impact on how atoms work and on how chemistry works, and therefore how biochemistry works, and therefore how we work, right? So we are in some very indirect chain, very sensitive to the frequencies of the universe, and so it's not a completely abstract thing for us. It matters.
Wow. So okay, so just to play with the thought here, if you took whatever the heaviest gravity mass is in the universe, I guess a black hole. Like if you took a black hole and you had an empty region of space, and I just snapped my finger rhythmically, and it appeared, disappeared, it would ripple. Gravitational waves would ripple from that, right? And they would propagate at the speed of light to everything around it. Would they also be rippling time? Like, is time, because it's connected to gravity? People would be like, whoa, I just got a lot of time. Whoa, a little bit. Whoa, a lot. Whoever got hit with that wave.
Yeah, I mean, this is not something we will likely ever. Well, I don't know. Maybe someday we'll measure it. It's not something we have measured. But yes, I mean, I'd rather than take your example of black holes coming out and in and out of existence, which couldn't actually happen.
Yeah, I was thinking what's something that could pluck the universe's gravitational wave, like the way you could a guitar.
But this is in fact what we observe. So two black holes, as they approach each other, if they are in orbit of each other over time, they will approach each other and they will spin faster and faster and faster, and eventually they will merge. And this rapid rotation followed by merger does indeed create gravitational waves, and we have measured them since 2015. And so we have hypothesized this for a long time, but now these are things these are measurements which are now done every few days. on Earth in the gravitational observatories that are in a few places on the globe now. And so, yes, indeed, these are ripples in space and time. Um, and so there are effects on distances, which are easy to measure and easy by, well, not easy to measure, but
Possible,
measurable. And
measurable.
the effects on time are there, but and we sort of know they're there because we have the equations for Einstein's theory. Everything is matching with our measurements extremely well, so we're confident that these things do happen. And but it happens that that's harder to measure than a change in the length of something. So the measurements that are actually made are really measurements of the rippling of space, but the rippling of time is also there. And one of the reasons we know that this kind of stuff happens to time is because there are other measurements which we can make which show these effects. One of the most obvious being the global positioning system satellites, which work on very highly precise timing, and there are both effects on time from motion and from gravity, and they're about the same size in this case. And you have to include both of them in order to correctly
Accurate
get the
ratings.
timing right. So every time you drive from one place to another, you are being guided by some little effects of the
Gravity and
curvature
time.
of gravity and
Yeah.
time. It's really there. We really use this is part of technology now.
Okay, let's talk about some of the definitions, because reading your book does kind of force you to like use some kind of words that you normally don't, like wavicle kind of popped into my head. But there's everyday meanings for particles and theories and waves that just seem like they're outdated or need to be updated for modern physics. Is that something we could chat about? Like why we
Yeah,
can't use the usual dictionary definitions for some of these terms?
it's not so much that things need to be updated as that, even in ordinary English, we run into this problem all the time, right? I mean, if you play baseball, you know that the word ball and striking out don't those words do not mean the same thing they mean in ordinary English. If you didn't know that, you'd be very confused when you're when you're overhearing the reporting at a baseball game, right? So these are really jargon definitions for ordinary words. And if you think about it, almost any field of life has that. I mean, I was listening to a couple of your podcasts not recently, and I mean, you're using all sorts of words, which sometimes I have to think about. Wait, what does he mean by that one? And this
I
is
don't know
just the
either.
way this is just the way human jargon works. And it's fine if the word is unfamiliar. Like when I say thermodynamics, your reaction is, will you tell me what that means, please? But if I say the word force, you kind of think you do know what that means because it's a word in English. And the fact that it kind of means something similar, but actually means something different, sort of it's made very precise by Newton. And then in modern physics, it takes on some new meanings. There's no way for you to know that. That's expert knowledge, right? So um, that makes it very important to my mind in a book like the one that I was writing to be super clear about these definitions. It's so easy when you're an expert to not really pay attention to that. I mean, if you're writing a book about baseball, are you going to define what a strike is? Or are you going to assume that your readers already know?
Right.
And, physicists often sort of assume, in a way they probably shouldn't, that people know what mass means and that they know what particle means and that they know what wave means. But when you look closely, you discover that, first of all, there are different definitions in English. You're not sure which one should be used. And second of all, in physics, the definition is often twisted or adjusted or expanded. And how are you going to follow a physics book if nobody's defined the terms? I mean, my gosh,
Right.
it has to be done. So I just felt this was extremely important, even at the base level, before getting into more complex things. And wavicles is yet another layer on top of that. But even a word like wave, I mean, I've been saying, particles are somehow waves, except that even in English, there's two different meanings for waves, right? So there's the wave you see at a beach, right? The wave you surf that's got one crest in the water, right? That's a wave, right? It's a shape like this. And the wave crashes onto the beach, right? That's what we mean by wave singular. But if you talk to a recording engineer or you talk about a sound wave, you're not meaning one wiggle in the water or in the air. You're talking about a set of
Pattern.
them, right? A pattern, exactly. So when you talk about a sound wave having a frequency, what you really mean is how often are these crests in this wave? How often are there wave crests passing my ears and making my ear flap, right? That when I say that electrons are really waves, I'm really talking about this more general thing, where something that have actually many different shapes and not just like a wave at the beach. And so, if you're going to go around saying, your book is called Waves in Impossible Sea, and you're going to start telling people that particles are really
Yeah,
waves,
like what's a
you
sea?
really better
What's
explain this,
impossible?
right? So, in some sense, one of the things that is really important about the fact that electrons and photons and quarks and all those other particles with funny names are really waves is that waves are much more flexible than particles. I mean, a particle is a dot. Okay, you take a particle, you take a grain of sand, you put it on the table. What does it do? Nothing. If I put it in a jar and I make the jar smaller, what does it do? Nothing. But if I put a wave somewhere, first of all, it can have a lot of different shapes. It could expand to fill its container. If I compress the container, it'll change its shape. It may vibrate up and down. It may splosh around. I mean, it can do a lot of things. And the fact that electrons can do so many things is really important in nature. So by calling them a particle, we are redefining the word particle, which is okay. I mean, we redefine words all the time. But it's kind of unfortunate
Yeah,
because the
you want to
word,
do it towards things that are accurate
yeah,
away from.
when you say the word particle, it brings in all this baggage about what we think that word means, which a lot of that baggage does not apply to actual electrons. So that's part of why, for me, the word particle is a particularly egregious example. But and why I sort of prefer the word wavicle, which is an old word, but didn't really get picked up for one reason or another. But no matter what word we use, it's important to understand that the word particle is being used in a sense where there's some things about electrons that are particulate, but there are a lot of things about them that are not. And this is true about a lot of the words that we use in physics. That the word that we use has meanings that doesn't have some of the meanings it has in English, and has some meanings that maybe it doesn't have in English. And sometimes, what even worse, it may have several different meanings in physics, which really makes things messy.
Right. One of the most interesting things about the way your book reads is that you spend some of those early chapters like you have to kind of get through a little bit of like redefining the words, thinking deeply about like what a wave is and like a crest and a kind of in terms of the universe what we're thinking about. And then later in the book, like all these cool pieces fit into place. So I can see why you made a point to try to, I guess, break it down like that, because it's not like I often listen to audiobooks that are like kind of over my head and
Mhm.
I walk away thinking I enjoyed it, but not really clicking too many times. And that might have been because you did a really good job setting up the way I should be thinking about some of these particles. So I think that effort was well worth it.
Good. I'm glad to hear it. I mean, it definitely was. It was very intentional that I wanted to make sure that the statements I would make late in the book, which are the really you know the heart of the matter, would have the proper foundation. Because otherwise, I think what happens a lot is that people who are interested in the subject might read one book and then they read some article in the newspaper, and people are using the same word to mean different things, and they end up completely confused. Like a famous example is that people will say Einstein said that the faster a thing goes, the more mass it has. Mass increases with speed. This is something which
Yeah, I've
some of
heard
us are
that.
taught in school. You will find it repeatedly in science journalism articles. It's not wrong, but it's very confusing when you also say at the same time that the neutron has a larger mass than the proton does. Because shouldn't that depend on how fast the proton is going if mass changes with speed? So the solution to this confusion is that physicists are using, or the journalists are using, two different meanings of the word mass. And
Yeah.
we don't learn about that in school because in Newton's day, there was only one definition and they were all the same. And one of the things that Einstein discovered is that the different ways of measuring mass that for Newton would have all given the same answer, they actually don't give the same answer. And so you have to actually give you have to define different types of mass, which means you're measuring how an object behaves when it's disturbed in different ways. You're getting different answers. So it's really important for the word mass, which is a lot of what my book is about, to be very clear about which definition is being used. And I hope that one of the effects of this book will be to encourage more science journalists to be really more careful
Yeah. Well, I mean,
about
you
how they're using
tore
this word.
like you tore into those guys that were saying it was like the Higgs particle gives mass like a popular person walking through a party and like attracting all the people
I'm
around him.
not
You were
fond of that.
like,
No.
No, you were like, this is so wrong, and everybody believes it.
Well, I mean, physicists don't believe it, right? I
Yeah.
mean, this is about how we communicate as experts to non-experts. And part of my goal in writing this book is to set a standard, which is that there should be no statement in a book on physics which fundamentally contradicts facts about physics, that goes against the basic equations. The purpose of the book is to explain what's in the equations. And if you don't do that, if you say things that are kind of compromises and they end up compromising some really
Hmm.
deep things, then when
It's
you
like a
try to explain
wobbly
those deep things,
foundation.
you can't make any sense of it. So what is the purpose? I mean, are we just trying to confuse everybody and make them, is it like those Holiday Inn Express commercials? We're trying to make people feel smarter? Or are we actually trying to give people an opportunity to understand how the world works? If we're going to do the
Yeah.
latter, we have to do it right. And we can't play these games where we say things that are sound kind of reasonable but are
Hmm.
actually wrong.
Right. I need, yeah, when I go to get a book, I need one shelf that's like it makes you feel smarter, but you're not going to be smarter, and one that's like it's going to make you feel stupid, but you'll be smarter. And like
Well, I
I'll
hope it
pick
won't make
that
you feel
second
stupid,
one.
or at least no more stupid
Well, it will
than
because it
we
makes you
humans are,
get
the rest of us
yeah,
are.
because it makes you realize how little you know. Whenever you think whenever you think you know something, it feels like there's more to learn.
Well, I mean,
But
that's certainly true for physicists too. I mean, there's
yeah.
that's and one of the other things I wanted to emphasize in the book is, sometimes some of these physics books give the impression that we figured it all out. I mean, nothing could be further than the truth. We have figured some of it out really well, but then there's just enormous amounts that are left over that are totally confusing. And a lot of the things that I mean, this point about steady motion not being detectable and being the same as being stationary. I mean, again, we understand that this is true. We do not understand why fundamentally the universe is built that way. And so, that's an area of ignorance. If you could explain why the principle of relativity has to be true, you would be learning something.
So if we did go through school and we built from the atomic model where everything was a particle, and then we went into chemistry and biology and worked our way up through the sciences, and now we go back and we realize we had sort of a shaky base, and we should really be thinking of a particle as something that's in a wave or a excitation in the quantum field. Um, does that mean the stuff above it needs to be kind of rethought too, or does it pretty much all still lock in after
That's a
that?
really good question, and the answer is that it depends. In some sense, um, there were inconsistencies in what we were taught in school, and we didn't notice them. And those inconsistencies get somewhat resolved by some of these weird things. Let's think about it this way. It's certainly true that complexities at a microscopic level often become unimportant at a macroscopic level. I mean, even just ordinary human life, most of the time, we don't have to pay attention to the fact that we're made from all these molecules. But DNA is not an essential piece of knowledge for going around and shopping at the shopping center. But on the other hand, understanding how at certain points DNA becomes pretty critical. It certainly affects how we reproduce and how we survive from day to day. So there are certain things that where you don't need to know it, but there are certain places where those microscopic details do matter. So for example, the fact that light is made from these wavicles or particles or photons is actually very important in how eyes work. The eye has molecules in it, and those molecules absorb light one photon at a time. So
Yeah, they're
if
not
you
objects
are,
hitting your eyeball. Yeah.
they're not particles hitting your eyeball. They are
Yeah.
waves that are being absorbed. What happens is the light wave comes in, the chemical of rhodopsin begins to vibrate and absorbs it. It changes its shape. It's important that it's absorbing a wave and that it's absorbing it one photon at a time, because that's the amount of energy that it takes to make the rhodopsin change its shape without breaking it.
Mm.
So, all these facts about photons, that light is made from photons, are actually critical in the very device by which we see. And so, what do you have to re-envision? Well, I mean, if your chemistry class told you that rhodopsin is a bunch of, atoms strung together like little balls, that's not so wrong. But what did it tell you about light? I mean, did they tell you light was a wave? Did they tell you the light was coming in photons? I mean,
Sometimes, yeah, sometimes
depends on your
not.
chemistry class,
Yeah.
right? So that's a place where these details actually matter for something that has macroscopic influence on us. Many details of basic chemistry do, in fact, depend, structure of molecules, the speed of certain molecular reactions, they do depend on these quantum phenomena, which where the wavical nature of things can be important. And so, you know, in some sense, as you go up in scale towards more and more macroscopic things and more daily life, fewer and fewer of those sort of depend critically in an obvious way on the fact that there are weird objects at the bottom that are really waves, except for the fact that all of the atoms depend on it. And since we're made from it, at some level, I mean, it's critical, right? So it sort of depends on your point of view. There's a lot of your day you don't need to know this, but there is no part of your day where you are not dependent on it.
The book, you often say, use the quote that we are waves of the universe. I have to start thinking of myself and what feels solid as something that's kind of a connected wave to the universe. But that also sounds a lot like what people say, like everything in the universe is an energy, or we're all connected, right, like as one. So it sounds sort of philosophical
in terms
and spiritual.
Of my own
Do you
philosophical
with,
thinking? I mean,
any of those thoughts?
Yeah, I mean, I think it's very meaningful. I wouldn't say, again, I'm careful not to say it's not that we are waves of the universe. We are made of waves of the universe, right? So it is an amazing thing, and appears to be true, right? That and what I'm saying here is not just some speculation. We see in experiments that the fundamental objects from which we are made are waves, and they're waves in these things called fields. We haven't talked about that much because they're a little hard to describe in a short time, but these fields are somehow integrated into the universe. So I don't know if we're literally waves of the universe, but we're certainly waves of something that's a part of the universe. And so, the fact that my entire body is built up out of 10 to the 28 atoms, a ridiculous number of atoms, each of which contains a large number of wavicles inside it. And those wavicles are ripples of something that's a part of the universe. I mean, this is telling me that I seem like some sort of separate thing in the universe, but it's just not true. I'm an instantiation of the vibrations of the universe, literally. And I think in a society where we often feel very alienated from the world in which we live, to appreciate the fact that no, we're actually a part of the world in which we live is meaningful. And so, I think each of us will find our own meaning in that. I think this is particularly important at a time where, just a few hundred years ago, we thought we were the center of the universe, and that the reason the universe was here was for us. And now, given what we know, I mean, we're on a not particularly interesting star in a not particularly unusual galaxy, and we're not in its center. We're off in some far off place, and we're not obviously at a particularly important time in the universe's history. So it's easy. I mean, if you think about movies like Everything Everywhere All at Once, which I thought was fantastic, one of the things it's really about is this sense of loss, that we no longer mean something because life is no longer meaningful because it was all for us. It has to be meaningful for some other reason. And I think it's a lot easier to make meaning of life and of living if you understand that you have emerged out of the universe. You're not just dropped down in it somehow. And so I think, it's a philosophical and as a spiritual piece of knowledge to take with you as you try to make sense of this world and try to find meaning in it and meaning in life. I think that has some value. And so it's certainly one of the things I wanted to convey in the book.
Awesome. Well, that's a beautiful way to end it. So thank you so much for your time, Matt. Your book is called Waves of an Impossible Sea. I have read it twice, maybe in another year or something. I'll probably revisit it because it really did sort of change the way I think, like literally, figuratively. And it's a wild ride through quantum fields, warp space, fields in particular we learn a lot about, and just the hypothetical possibilities that we could be solving over the next few decades. Anyone who really enjoyed this conversation and wants to learn more, you can peruse the website. You can read his blog at profmattstrassler.com. There's a link in the description below. So Matt, thank you so much. I appreciate you spending time with me. That was a wonderful conversation. And
it's been a lot of fun.
Yeah, it really has been. So hopefully we'll get a chance to chat again soon, and good luck with everything, and we'll talk to you next time.
All right. Thanks so much.
Okay. Bye.